In this lecture, we determine an equation of the plane that passes through three non-collinear points P, Q, and R. A basic fact from Euclidean geometry states that there is a unique plane that contains three non-collinear points, that is, if the points do not lie on the same line. Let us call the plane that contains the 3 points P, Q, and R S, that is, if P, Q, and R are non-collinear. Assuming that they are non-collinear, then there are quite a few elementary ways of finding the equation of the plane S. In this lecture, we will use two different methods to find an equation for the plane S. For the first method, we simply plug in the coordinates of the points into the general equation of a plane. The general equation of a plane is ax plus by plus cz equals d, where a, b, c, and d are real numbers. An added condition is that a, b, and c must not all be equal to 0. This last condition is equivalent to the equation a squared plus b squared plus c squared is not equal to 0. Plugging in the coordinates of p for x, y, and z in the equation of the plane, we get the equation a times 3 plus b times -1 plus c times 2 equals d. The coordinates of q lead to the equation a times 2 plus b times 2 plus c times -3 equals d. And the point R leads to the equation a times 2 plus b times -3 plus c times 3 equals d. And so we have a system of 3 equations and 4 unknowns. With 3 equations and 4 unknowns, we try to solve for the first 3 variables a, b, and c and see what we get. We can try solving for a, b, and c by hand, which would be an elementary exercise. We can also use a graphing calculator or a computer software to solve for a, b, and c. Doing so, we get a equals 7d divided by 17, b equals minus 6d divided by 17, and c equals minus 5d divided by 17, so that a, b, and c are in terms of d. With 4 unknowns and only 3 equations, we could have tried solving for any 3 of the 4 unknowns and hope for a solution in terms of the 4th variable. A sure way to find out if there is such a solution and to find the formulation for the solution is to use what is called matrix row reduction on the system and get an echelon form of the augmented matrix of the system of equations. We leave that as an exercise for the viewer. In a situation like this one, where we solved for a, b, and c in terms of d, d may be referred to as a parameter. It is also often called a free variable. With d being a free variable, it means that we can choose d to be any non-zero real number. To avoid fractions, let us choose d to be equal to 17. Therefore, a equals 7, b equals minus 6, and c equals minus 5. And so, an equation of the plane S is 7x minus 6y minus 5z equals 17. The second method that we will employ uses vectors. The image on the right shows the 3 points P, Q, and R lying on the plane S. We take the vectors PQ and PR. The cross product of these two vectors is a vector that is normal or orthogonal to the plane S. In other words, the cross product of PQ and PR is perpendicular to S. Let us call this cross product vector n. Any vector that lies on the plane S will be perpendicular or orthogonal to the cross product of P, Q, and PR. So if we take a general point M whose coordinates are x, y, and z on S and take the vector Pm, the vector Pm will be orthogonal to the cross product N. With N being orthogonal to Pm, the dot product of N and Pm, which we symbolically write as N dot Pm, is equal to 0. This is the preliminary form for the equation of the plane. We first find the components of the vector N. For this, we need the components of PQ and PR. To find the components of PQ, we simply take the coordinates of Q and subtract the corresponding coordinates of P. So the vector PQ is made up of 2 minus 3 for the first component, 2 minus 1 for the second component, and minus 3 minus 2 for the third component. So PQ is the vector -1, 3, -5. Similarly, the components of the vector PR are obtained by subtracting from the coordinates of R the corresponding coordinates of the point P. And so PR is made up of 2 minus 3 for the first component, minus 3 minus 1 for the second component, 3 minus 2 for the third component. So that PR is the vector -1, -2, 1. So now we can write the determinant representation of the vector N, or the cross product PQ cross PR. N is equal to the determinant of the matrix, whose first row is made up of the vectors I, j, and k. The second row is made up of the components of the vector PQ, and so we have -1, 3, -5. The third row is made up of the components of the vector PR, and so we have -1, -2, 1 for the third row. Let us use 2 by 2 submatrices to evaluate this determinant. So the first component will be the determinant of this 2 by 2 submatrix. So we have 3 times 1 minus -2 times -5. The second component is equal to minus the quantity -1 times 1 minus -1 times -5. The third component is the determinant of this 2 by 2 submatrix, so that we have -1 times -2 minus -1 times 3. Simplifying, we get the vector -7, 6, 5. The only thing we need is the vector Pm. We get the components of Pm by taking the coordinates of M and subtracting the corresponding coordinates of P. And so the vector Pm has components x minus 3, y minus 1 or y plus 1, and z minus 2. And so the dot product of n with the vector Pm is equal to -7 times x minus 3 plus 6 times the quantity y plus 1 plus 5 times the quantity z minus 2. And because the two vectors are orthogonal, the dot product should be equal to 0. Simplifying, we get -7x plus 6y plus 5z equals -17.